Hello everyone, welcome to Masterspharma Academy. Hope you are doing good. In today's session, we will discuss about some pharmaceutical analysis MCQs. Here we go. The first question. In UV visible spectroscopy, a hypsochromic shift is most commonly caused by options. Option A, increased conjugation. Option B, decreased polarity of solvents. Option C, protonation of an amino group. Option D, increased temperature. The correct option is option C, protonation of an amino group. Why protonation causes a hypsochromic shift? A hypsochromic shift in UV visible spectroscopy refers to an absorption moving to shorter wavelength. It is an higher energy. This occurs when energy gap between HOMO and LUMO increases. Now we see the other options. Increased conjugation. It is incorrect because more conjugation lowers the energy gap and producing a bathochromic shift. It is a red shift, not an hypsochromic shift. Option B. Generally, it is incorrect because for most transitions, increased solvent polarity gives a bathochromic shift and decreases the polarity does not typically causes a strong hypsochromic shift compared to structural changes. Yeah, here option D, it is incorrect because increased temperature affects band broadening, not the wavelength position in a consistent or a meaningful way. So the correct option is protonation of an amino group. The second question, the most commonly used detector in HPLC with gradient elution is options. Option A, refractive index detector. Option B, UV detector. Option C, fluorescence detector. Option D, conductivity detector. The correct option is option B, UV detector. UV detector, especially a diode array detector, works very well because most common solvents used ingredients like acetonitrile, methanol and water have low UV absorbance. So it is commonly used detector in HPLC. Now we see the other options. Refractive index detector. It is not suitable because refractive index detectors are highly sensitive to change in mobile phase composition. During a gradient elution, the baseline becomes unusual. Thus, RI indictors are only used in isocratic HPLC. This is the worst detector for gradient works. Now the option C, fluorescence detector. It is very sensitive but not universal. It works only for the fluorescence compounds. Option D, conductivity detector. Conductivity detector, it works mainly for ion chromatography, not standard gradient for HPLC. The next question. In NMR, downfield shifting is due to options. Option A, increased electron density. Option B, shielding. Option C, de-shielding. Option D, spin coupling. Here the correct option is option C, de-shielding. Why de-shielding causes downfield shift? When electron density around a proton decreases, the electron magnetic field is felt more strongly. Thus, increases the required resonance energy, leads to peak moves the downfield. Now we see the other option. Increased electron density leads to more electron density, leads to more shielding, and it causes the upfield shift. Option B, shielding. Shielding moves peak upfield opposite to the downfield. Option D, spin coupling only. Coupling changes the splitting pattern but not the chemical shift value. So the correct option is de-shielding. The next question. Raman spectroscopy is based on absorption of UV light, molecular vibration with Stokes and anti-Stokes scattering, infrared absorption and electron spin transition. Here the correct option is option B, molecular vibration with Stokes and anti-Stokes scattering. Raman spectroscopy works on the principle of inelastic scattering of monochromatic light, usually a laser light. When light interacts with molecule, most photons undergo ray light scattering. It is the energy changes. Stokes lines is equals to photon losses and energy. Anti-Stokes lines is equals to photon gains energy. This shift corresponds to molecular vibration and energy level. Here we see the other options. Option A, absorption of UV light. It is incorrect because it is an UV visible spectroscopy, not Raman spectroscopy. Option C, infrared absorption. It is incorrect. This is IR spectroscopy where molecular absorb IR radiation, not the scattering. Option D is electron spin transition. It is incorrect because this is a EPR by ESR spectroscopy and not the Raman spectroscopy. So the correct option is option B. The next question, in complexometric titrations, the most widely used indicator is option A, phenolphthalein, option B, methyl orange, option C, aerochrome black tea, option D, fluorescence. Here the correct option is option C, aerochrome black tea. In complexometric titration, especially in EDTA titrations, the most commonly used indicator is aerochrome black tea. It forms a wine red complex with metal ions like calcium and magnesium. At the end point, when EDTA binds the metal ions, the indicator is released and it gives a clear blue color. This color will changes from wine to red and red to blue and makes the EBTA the standard indicator in hardness and metal ion titrations. Here we see the other options. Phenolphthalein is used in acid based titrations, not in complexometric titrations. Option B, methyl orange. It also used for acid based titrations, not in EDTA titrations. Option D, fluorescence. It is used in precipitation titrations, not in complexometric titration. The next question. The term LOD, limit of detections, represents option A, lowest concentration that can be quantified. Option B, largest concentration measurable, lowest concentration that can be detected but not quantified. Option D, highest noise cancellation. The correct option is option C, lowest concentration that can be detected but not the quantified. At the LOD level, signal is equals to 3 times of the noise. The analyzer produces the detectable responses. Precision is too poor to report it numerically, not quantifiable. This is why it's called the detection limit, not the quantification limit. Now we see the other options. Option A, lowest concentration that can be quantified. This is the LOQ, limit of quantification, not the LOD. LOQ is equals to 10 times into the noise. Option B, largest concentration measurable. Largest concentration measurable refers to the upper limit of the calibration curve, not the LOD. Option D, highest noise signal. Highest noise signal leads to noise random background signal. LOD is based on distinguished analyte signal above the noise, not noise itself. So the correct option is lowest concentration that can be detected but not the quantified. The next question. Linearity in analytical method validations refers to option A, extended to which results vary, ability to provide results proportional to concentration, ability to detect small changes, and stability with time. The correct option is answer B, ability to provide results proportional to concentration. Here, linearity in analytical method validation means the method ability to produce test results that are directly proportional to analyte concentration within a given range. This means when concentration increases, the response peak area and absorbance increases in a straight line relationship demonstrated by a linear calibration curve with a higher concentration. Now we see the other options. Option A, extent to which results vary. This describes the precision, not the linearity. Option C, ability to detect small changes. This refers to sensitivity, not the linearity. Option D, this stability with time. This refers to stability and it also refers to the not linearity. So the correct option is ability to provide results proportional to concentration. The next question. A primary standard substance must have options: high hygroscopicity, high molecular weight and stability, volatile nature, and poor solubility. The correct option is option B, high molecular weight and stability. A primary standard is a highly pure substance used to prepare standard solutions in titrations to ensure accuracy. It must meet the specific criteria. In option B, high molecular weight and stability, a primary standard must have high molecular weight to minimize weight errors, high purity and chemical stability, so it does not degrade over a time, non-hygroscopic and non-volatile. Here are the examples of anhydrous and silver nitrate. Now we can see the other options. Option A, high hygroscopicity. Substances absorb moisture and it leads to weight become inaccurate. Option C, volatile in nature. Volatile substances evaporate and leads to unstable and it not suitable. Option D, poor solubility. Primary standard must dissolve easily for accurate titrations. The next question, the HPLC pump type commonly used for gradient elution is option A, syringe pump, option B, reciprocating pump, option C, peristaltic pump, and option D, gear pump. The correct option is option B, reciprocating pump. Yeah. Reciprocating pump is used as a piston moving back and forth to draw and pushes the solvent. Its advantages are high pressure capability, accurate precise flow rate and compatible with mixing system. Now we see the other option, syringe pump. It delivers very smooth flow but not suitable for gradient mixing and it is used for in LC and MC infusions and also in nano LC. The option C, peristaltic pump. It cannot deliver high pressure flow and it is pulse and noisy and not suitable for HPLC. Option D, gear pump. It gives constant flow but low pressure capability, not suitable for high performance column. So the correct option is reciprocating pump. The next question. Conductivity in solutions increases with options large molecules, option B non-ionized species, option C concentration and mobility, option D viscosity increases. So the correct option is ionic concentration and mobility. In conductivity of solutions depends on how many ions are present and how fast they move under an electric field. Conductivity is directly proportional to number of ions into mobility of ions. Conductivity increases when more ions are present, higher concentration, more ions is equals to more charges, charge carriers leads to higher conductivity, higher mobility. When mobility increases, when temperature increases, solvent's viscosity decreases, ions are smaller and lighter, both factors are directly conductivity. Here the option, now we see the options. Option A, large molecules. It is incorrect because they are usually non-ionic or bulky and do not conduct electricity. Option B, non-ionized species. They produce non-ions and zero contribution to conductivity. Option D, viscosity increases. Higher the viscosity is equals to thicker solvents and it leads to ions move slower. Yeah. This is for today's session. Thank you for watching. For more such content, please consider subscribing and follow us on Instagram, masterspharma.